Hello. In this presentation, I will be discussing one of the 10 reactions in Chapter 5, 9 of which, if you remember, are addition reactions. The first of the addition reactions is called hydrohalogenation. The reagent that we use is very simple, either HCl, HBr, or HI gas. Typically, we'll be using HCl and HBr because they work a little bit better than hydrogen iodide. The generic reaction, as you can see, involves starting with an alkene. So literally we'll take a bottle of some alkene from the stockroom and put it in a flask with some solvent, and we will add some HCl or HBr or HI, and we'll convert it into a different compound. This is called an alkyl halide or haloalkane because we have a halide with an alkyl group attached. Otherwise, we can think of it as an alkane with a halo group attached. So alkyl halide or haloalkane. This is a family of compounds much like alkenes and alcohols and other families of compounds, and it's always the product of the reaction of HX or HCl, HBr, HI with an alkene. So here are some examples. If we start with 2-butene and we add HCl to it, we end up with the double bond disappearing, this hydrogen getting a new hydrogen, so it's now CH2, that carbon getting the chlorine from the HCl. And notice we could have added the other way around as well. That carbon could have gotten the hydrogen, and that carbon could have gotten the chlorine. And in this case, it's the same product either way. Another example, starting with cyclopentene, if we add HBr to it, one of these two carbons gets the hydrogen, so that's this one, and you'll have to imagine this carbon has one hydrogen. Now that we've added the hydrogen from the HBr, now it has two hydrogens. And the bromine from the HBr adds onto this carbon. It had one hydrogen, it still has one hydrogen, but now it also has a bromine. In both cases, the product we get is an alkyl halide. This one specifically is an alkyl chloride. This one specifically is an alkyl bromide. This one happens to be a cycloalkyl, but still considered an alkyl group. Here are some more complicated examples. Notice that this alkene, the two carbons of the double bond are not the same as each other. This is propene. This is a CH2 on this end, but a CH with a methyl on this end. If we add, let's say, HI to it, do we add the hydrogen to this carbon and the iodine to that carbon and make the double bond disappear? Or do we add, and that would give us this product, or do we add the hydrogen to this carbon and the iodine to this carbon and get rid of the double bond, and that would give us this product? Well, in fact, there's a rule for that. To decide which carbon gets the hydrogen and which one gets the halogen, we use something called Markovnikov's rule, and it will predict which of these two products will be the major product in this case. What Markovnikov's rule says is, or at least the way he stated it, was them that has gets. That is, the carbon with the most hydrogens already gets the new hydrogen. So, notice that this carbon has one hydrogen. This carbon has two hydrogens. Therefore, when the HI adds this carbon, which already has more hydrogens than that one does, this carbon gets the new hydrogen and it becomes CH3. This carbon that didn't have more hydrogens picks up the other thing, which in this case is the iodine, so it becomes that product. Therefore, using Markovnikov's rule, we have predicted that this will be the major product. Here are some more examples. If we start with 2-methylpropene, notice 3 carbons with a double bond is propene and a methyl group on the second carbon, and we add HCl to it. Don't forget, that's a CH3 here, so that's a methyl group, that's a CH3, so that's a methyl group. That's just carbon with no hydrogens, and that's a CH2 on this end. Again, these polygon figures can be a little difficult to interpret, but remember, each carbon has to have enough hydrogens to make a total of 4. If we take 2-methylpropene and add HCl to it, will we add the chlorine on this carbon and a hydrogen there to produce that product, or would we add the hydrogen on this carbon and the chlorine there to produce that product? Markovnikov's rule says add the hydrogen to the one that already has the most hydrogens, so it's going to be this carbon, so that CH2 becomes a CH3. This carbon then gets the other thing, which in this case is chlorine. Since it doesn't have any hydrogens to begin with, it just picks up the one chlorine, and this then is the product that we would get. That would be called 2-chloro-2-methyl propane, otherwise known as T-butyl chloride. Here's another example, starting with 1-methylcyclopentene, and we add HBr to it. See if you can predict which carbon, that one or that one, gets the new hydrogen, and therefore which one gets the bromine. If this is what you predicted, that is correct. This carbon, having one hydrogen, picks up another one and becomes a CH2. This carbon, having no hydrogens, picks up the bromine, and the bromine ends up there. Here's another example. This one's a little bit more complicated. Notice that in this alkene, 2-pentene, that carbon has one hydrogen, and that carbon has one hydrogen. This one also has a methyl, and this one has an ethyl. So it's non-symmetrical, but both carbons have the same number of hydrogens. What would Markovnikov have to say about that? He would say, well, we can't tell the difference. At least the HCl can't tell the difference. So whether the hydrogen goes here and the chlorine there, or the hydrogen here and the chlorine there, is not predictable. Therefore, probably we're going to get roughly equal amounts of the two products. That would be this one and this one. And since the two ends of the alkene are not the same as each other, the two alkyl halides we get are different. This is 3-chloropentane. This is 2-chloropentane. So now you know what the story on regiospecificity, in other words, which carbon gets which group when we add HBr or HCl or HI to a double bond. Now we're going to talk about stereospecificity. The question is, do the hydrogen and the bromine both add to the same side of the double bond? In other words, both to the top or both to the bottom? Like this. So notice the hydrogen added on the bottom and the bromine added on the bottom, so those are both dotted lines, and that forces the methyl group up on this carbon and the methyl group up on that carbon. So this is what's known as syn addition. In this particular case, this is a chiral compound, and so we end up with both enantiomers of it. This one would arise from adding the hydrogen and the bromine on the bottom. We could just as well have added the hydrogen and the bromine on the top, and that would give us the enantiomer. But that would be the product. These two, this and its enantiomer, would be the product of syn addition. Or do the hydrogen and the bromine add on opposite sides. So one hydrogen adding on the top and one bromine adding on the bottom, or vice versa. If so, this would be our product. Notice the hydrogen is pointing down on this carbon, and the bromine is pointing up on this carbon, so the hydrogen must have added to the bottom, and the bromine must have added to the top. That forces this methyl group up, and that methyl group down. This is what's called an anti-addition. If the hydrogen and the bromine add on opposite sides, that's called anti-addition. If the hydrogen and bromine add on the same side, either the bottom or the top, that's called syn addition. This would be the product of anti-addition, and again, it happens to be chiral, so we would get both this compound and its enantiomer. This one from adding the hydrogen on the bottom and the bromine on the top. The enantiomer would arise from adding the hydrogen on the top and the bromine on the bottom, so we get the mirror image in that case. But anti-addition would give both of those products. So the question is, do we get syn addition or anti-addition? Here's the product of syn. Here's the product of anti. Each also has an enantiomer. In point of fact, both sets are formed about equally in this reaction. So we get both syn and anti-addition. When this happens, it's called non-specific. In other words, it doesn't specify syn or anti, and so you get both. Be aware, other reactions, other addition reactions will be syn, and some will be anti, and some will be non-specific. This one just happens to be non-specific. Okay, so now we understand the data with this reaction. We understand that it always goes by Markovnikov addition, and we understand that it always goes by non-stereospecific. In other words, you get both syn and anti. So what we want to do now is understand the mechanism and explain why these occur and what are the steps by which hydrohalogenation occurs. Here is the overall reaction. I've written it in a generic form here so that the four groups that are attached to the double bond are not specified. This is not to specify these are methyl groups in this case. These are just to specify that there may be hydrogens and other carbon groups and so on. And we're going to add HX, which is a generic, could be HCl, HBr, or HI. And we see the hydrogen adding on one and the halogen adding on the other. So that's the overall reaction. Okay, so here we go with the mechanism. First step, the HX acts as an acid, and it's going to donate an H plus to the double bond. So one of the two carbons of the double bond is going to act like a base and pick up the H plus. So we're going to form a new bond between the hydrogen and the carbon. The double bond is going to move into here to form that bond. In other words, one pair of electrons from here is going to move into there to form that bond. That leaves this bond without a second pi bond between us. This is now just a single bond, but by having taken these two electrons away from the bond, it removes one electron from this carbon, so it ends up with a positive charge. Of course, the halogen, having given away its H+, in other words, the conjugate base of this acid, is X-, so we end up with a positive carbon and a negative halogen. So notice that this first step is really just an acid-base reaction. This is the acid, donates its hydrogen to this material, forms a new bond, forming something positive, and the conjugate base is the X-. So that's always the first step in the hydrohalogenation mechanism. The second step is very simple. Once you've formed a positive carbon, then the negative halogen is going to donate a pair of electrons in between here and form a new bond, and so we get a bond between the carbon and the halogen. So this is really just a falling together of a positive ion and a negative ion, and the negative donates a pair of electrons in to form that bond. So we end up with a product. That's the that you get for the product. So that's it. That's the whole mechanism. And notice that the two steps add up to the overall reaction. If we cancel out anything in these two steps that appears on both sides, well, this does, so we'll cancel that. This does, so we'll cancel that. That leaves us with the alkene starting material and the HX and the alkyl halide final product. And so this is the balanced equation. As always, the individual steps of the mechanism have to add up to the overall reaction. Here's an energy diagram. Notice that because it's a two-step mechanism, we have two hills in the mechanism. Notice at this point right here, that's the intermediate. That is this ion pair, positive and negative ions separated from each other. That's a high energy situation because positives don't want to be separated from negatives. They want to be together if they can. And so that's a high energy material. Plus, if you'll notice, this carbon does not have an octet, and therefore this is a relatively unstable, relatively high in energy material. In between, as the bond is breaking, we have a hill that we have to go over, and then we get to the intermediate, which is this. And then that intermediate, which is this, does another hill that you have to go over. As I've suggested in this energy diagram, you can tell two things about the reaction. First of all, the first of the two steps is slower. In other words, it's harder to break a double bond and form a new single bond and form a positive charge. That is slower than it is for two ions to simply fall together and form a new compound. So this is the slower step of the two. This is the faster step of the two. That's a higher hill. That's a lower hill. The other thing you can tell is that it's an exothermic reaction overall. From here to here is from here to here. That's downhill, and therefore it's an exothermic reaction. Now, next question. Why does the Markovnikov rule work? Well, consider the following steps and what choices we have to make. The first thing is that an H+ adds on to the molecule, giving us a carbocation. This thing, because it's a positive carbon, only has 3 bonds to it. It does not have an octet. This is what's called a carbocation. So in the first step, the H+ is going to add on to form a carbocation. Here's number 2. Very important rule. We will use this over and over again. If you're comparing the stability of carbocations, tertiaries are the most stable, followed by secondaries, with primary carbocations being the least stable. In other words, if you have a choice, you want to form a tertiary carbocation rather than secondary or primary. If you don't have a choice but to make a tertiary, then you certainly want to form a secondary rather than a primary if you have a choice. Okay. So, as I said, if it has a choice, the H+ is going to attach to the other carbon, giving the more stable carbocation. And then finally the halogen adds wherever the positive charge was to begin with. And since this will likely be tertiary, if that's possible, we'll end up with a tertiary alkyl halide. If this has to be secondary, rather than, because there's no choice of forming a tertiary, then it will be form a secondary carbocation. And if it finally has no choice other than to be primary, it will of course form a necessarily primary carbocation. So let's predict the product of hydrohalogenation of propylene, and we can use the Markovnikov rule to predict it, which I've suggested of the two possible products. This is the major product based on the Markovnikov rule. But what we want to do is look at it in terms of the mechanism and see if we can understand why this is the major product. So first, let's write the mechanism of both reactions. What would the mechanism for formation of this product be? And what would the mechanism for formation of this product be? Notice that even though this is not the major product, we can still write a mechanism for its formation. And then what we'll do is compare the two mechanisms and see which one's better. And hopefully the one that forms this is better since we know it's the major product. Okay, so for the first reaction, the alkene reacts with the HX in the first step of the mechanism. The hydrogen is going to go in the CH group right here, and that's going to leave the CH2 with a positive charge. And then that positive CH2 is going to fall together with the X- and form the bond here. That would give us the primary carbocation, which would be this product. The second reaction, that is this one, the HX adds its H plus onto this carbon instead, so that becomes a CH3. That leaves the other carbon positive. That's this one, and that's a secondary carbocation. And then, of course, the X- adds on wherever the positive charge was, so it ends up attached to the middle. What's the difference between the two mechanisms? The only difference is, in this one we're forming a primary carbocation, in this one we're forming a secondary carbocation. Clearly it's better to form a secondary carbocation since, as we learned a minute ago, secondary carbocations are better than primary carbocations. And notice also in this case there's no possibility of forming a tertiary carbocation, so that's not an option. But secondary better than primary, this mechanism better than that mechanism, therefore this product formed faster than that product. Okay, so basically, going back to that slide, what we've done is used the mechanism to explain the Markovnikov rule. Second question, why is the stereospecificity of the hydrohalogenation always nonspecific? Well, let's draw the alkene in a generic sense, so we're not specifying what these groups are on here, just that there are 4 groups, 2 on this carbon and 2 on this carbon. I've drawn it parallel to the floor, or tipped a little bit so that we can see the top and the bottom of the face of the alkene. We can, first of all, we're going to protonate it, and let's say the hydrogen attaches to the top, and so here's the hydrogen now having attached to that carbon on the top. That leaves this carbon as the carbocation, and notice that that's sp2, it's flat. This carbon is tetrahedral, but this one is flat, sp2 hybridized. So in the next step, the second step of the mechanism, where we're going to attach the Br-, the question is, will it attach to the same side the hydrogen added onto to begin with, or will it add to the bottom, the opposite side from where the hydrogen added on to begin with? In other words, will it add in a syn fashion, same side, or anti-fashion, opposite side? Well, the fact is there's really no preference for one or the other, so the bromide could add to the top or it could add to the bottom. Because this is a flat carbocation, the bromine doesn't care. The spaces are the same as far as it's concerned, and so it could add to the top just about as easily add to the bottom, and therefore we're going to get both products, and therefore it's non-specific. Now, here are some additional molecules for you to look at and see if you can draw the products. You might want to freeze the frame at this point and write those down, and just for fun, see if you can predict the products in both regiochemistry, where it's important, and stereochemistry, where it's important.